Hello everyone, welcome back. We have 11 lectures down, 27 to go. Unfortunately, we're doing this via YouTube because we have class canceled on the Wednesday and Friday this week. So, yeah, we'll record the videos. In terms of the videos, I'd recommend watching the pre-class video, taking a break, and then eventually watching this video as well. And we'll go through some clicker questions. Obviously, we can't do it in real time, but you guys will be able to get the content nonetheless. And so, yeah, class is canceled Wednesday and Friday this week. Also, no recitation on Thursday, but the TAs did put the recitation homework up on the Canvas website, so you guys can take a look at it and have some additional practice problems. All right, other stuff, second exam, still going to be on October 18th. We'll cover chapters 12 and 13. We're doing these recordings so we don't get behind schedule, and also so we can not rush for other course content. So we'll have these videos to stay on schedule. All right, equation sheet for exam 2 is up on Canvas. You can take a look at that, particularly when we start talking about integrated rate laws. Those will be very useful. Also, suggested chapter 12 practice problems are up on Canvas if you guys want to take a look. Other things canceled for today is we were supposed to have Ask a Scientist Gaming tonight. That will not be on. Kelly Farquharson, speech pathologist, speech/language pathologist, and also does interventions in speech therapy and things like that. But yeah, that will not be happening tonight. So we're going to postpone that until October 2nd. That's next Wednesday, assuming we have power and everything's back to normal. But yeah, mark your calendars for that because that should be should be fun. All right, so continuing our journey in chapter 12. So we covered chemical reaction rates and factors affecting chemical reaction rates. Now we're getting into rate laws. And so on Monday, we had a couple questions related to this particular set of data. We said, here's our change in concentration of A with respect to time. And we did a couple different questions. One was, what is the rate of disappearance of A with 1 second? What's the disappearance of A in the first 3 seconds? And we got two different answers, right? And so if we do the math, change in concentration over change in time, change of 5 molarity per second gives us 5 molarity per second. First 3 seconds is 10 minus 1.25 divided by 3 gives us roughly 3 molarity per second. And so one of the hardest parts about this is when you're trying to report this, how do you report how fast this reaction is? Do you use this number or do you use this number? When you're trying to compare to someone else and you've come up with a new best way to do something, I mean, obviously you're going to higher number is better, but that doesn't generally describe the reaction. And so we need to do something slightly different. And so for those of you that recognize this equation down here, change in concentration to change in time, turns out this is just a slope calculation, right? It's change in x over change in, or change in y over change in x. And so you can do this slope for any given point on this curve, but because it's curved, you're going to get different numbers as it progresses. And so the problem is the rate changes with concentration, just like we just saw. The numbers are different. And so what we need to do is have a more general way to describe this reaction, because we can't just say it's this number, it's this number, it's this number, because they're all right, and they're also not universally descriptive of this reaction. And so something we can do with this data is we can take our given time and our concentration and calculate an instantaneous rate. Basically, it's the slope of the line at any given point on that curve. And so we get the number changing. You can see here the rate decreases as the reaction progresses. As there's less reactant, that's generally what's going to happen in reactions. But again, this number changes, so it's not a universal descriptor. But it is proportional to concentration. And so what we can do is we can graph concentration versus rate, and all of a sudden we see a straight line. And straight lines are awesome, especially in the sciences, because it allows you to predict, right? If you know any 2 points, you can predict any point on the inside or extrapolate on the outside, but it does give you a testable hypothesis. And so straight lines are described by this equation, y equals mx plus b, y being the y-axis, x being the x-axis, m being the slope of the line, and then b being the y-intercept. And this is all you need to describe a straight line. And so if you know slope and b, the intercept, you can use any x to predict y, you can use any y to predict x and calculate your answers from there. And so in this particular case, this equation here translates to this equation here, where rate, which is the y-axis, is equal to k, the rate constant, times the concentration Br plus 0. And so this slope is a new factor that we're introducing. And basically it's a proportionality between rate and concentration depending on the dependence of that concentration. And so what's nice about this, and you'll notice you can calculate this slope for the entire data set or at each individual point, and you are always going to get the same answer. It's going to be 3.5 times 10 to the minus 3. And so this is why we like this K, the slope of the line, because it's a rate constant. It's a constant for the reaction. It's a proportionality between the reaction rate and the concentration, and it stays consistent throughout. And so rather than having to report a bunch of different numbers or number with respect to concentration, this rate constant is a general descriptor for the rate of reaction. And so if you want to compare apples to apples of the same reaction, report the rate constant rather than rate or at given concentration. And so this comes back to this idea of rate laws. And so broader picture of what the thing we just determined is from the slope of the line is a rate law. And so for any given reaction, A plus B giving products of some kind, you write a rate law that says rate is equal to K, the rate constant, times the concentration of reactant 1 to the X, reactant 2 to the Y, reactant 3, so on and so forth. And so this is the rate law for a reaction. It's the relationship of concentration and the exponents times the rate constant gives you the rate of the reaction. And so a couple rules to note about rate laws. They are defined in terms of reactants, so whatever is on the left side, not what's on the right side. And so remember our concentration equations, we talked about rates. There's a rate of disappearance, there's a rate of appearance, but for rate laws, it's always described in terms of the reactants. This X and Y are the order of the reactions. They are not necessarily the same as stoichiometry. They could be the same as A and B, but that would be a coincidence. X and Y are much more descriptors of a particular reaction. And so something important to note is these X's and Y's can only be determined experimentally. And so like we said, those X's and Y's are the order of reaction. It basically tells us for this rate limiting step, or what's actually happening in the reaction, these X and Y's tell you something about the species involved. And so they're described as something called the order of the reaction. And so depending on what this number is, it's going to be X order in A. So if it's a 1, it's first order. If it's 2, it's second order. 3 is third order, so on and so forth. And Yth order in B. So if this is a 1, first order, 2, second order, 3 is third order. And if there's a 0 here, basically says it's not dependent on the concentration of B, and so that's not included in the rate law of the reaction. But again, this rate law is related to an experimentally determined thing, not just the stoichiometry, but how the reaction actually happens and what the rate limiting step of the reaction is. And so here's just an example. F2 plus 2 ClO2s gives you 2 FClO2s. So the rate law for this reaction is actually this. Rate is equal to rate constant F2 to the 1, ClO2 to the 1, first order in F2, first order in ClO2. But you'll notice that this 1 is different than the stoichiometry because these X and Y's are not dependent on the stoichiometry of the reaction. Instead, the rate law looks something like this. And so what this tells us is something about the actual reaction. And it's important. Like, this equation still holds true, right? Whatever the stoichiometry of A and B, that's necessary to get to the product, but it doesn't tell you what's happening in the slow step of the reaction, which is what the rate law does. And so what it basically tells us is that one of these F2s interacts with a ClO2, and that's the slow step of the reaction because it's first order in both of those, and then something happens, and then eventually it incorporates the other ClO2, and it'll get you to the products. And so you still need 2 of these ClO2s to make it happen, but in the rate limiting test step, or the slow step of the reaction, these 2 are involved in the process. And so again, take home message, X and Y are not dependent on stoichiometry in this equation. They must be determined experimentally, or they must be given to you, right? You can't just look at a formula and figure out what X and Y are. And so in terms of how to determine those, there's a couple different ways you can do it. You can do it by inspection or by equation. It's totally up to you what you feel best with, but basically you need a data table that looks like this either way. You need to have concentrations of the 2 reactants, F2 and ClO2, and then you need to measure the rate of the reaction. In this case, we'll do the initial rate, what happens right away. And so what you need to do is basically fix one of the variables, change the other variable. So in this case, if we're going to compare, if we want to figure out X and Y, we basically need to compare these 2 reactions here. One where we kept F2 constant, and the second one where we changed ClO2. So we change it from 0.01 to 0.04, and then we measure how the initial rate changes. And so what we'll notice here is that, if F2 is constant and this is multiplied by 4, we see the rate here is increased by 4. And so that basically tells us rate is directly proportional to ClO2, which means this has to be Y. right? And so if this goes up 4, this goes up 4, this goes up 2, this goes up 2, the only way that's possible is if this number right here is 1. If this number here was 2, if we double this, we'd quadruple this. And so the only possible answer is y equals 1. And so we can do the same thing for the F2, trying to figure out what the exponent on F2 is. We keep ClO2 constant. We double this, see what happens to the rate. The rate doubles, basically tells us those two are also proportional, and so x equals 1. And so this is the data that you need to figure out what these exponents are. In this case, y equals 1, x equals 1. That gives us the rate law for this particular reaction. And so you can also do this algebraically, which is basically what we did descriptively just now. You can set up a proportionality between any two experiments. And so it's doing exactly what we just did. Find an experiment where H2 is constant, NO changes, the initial rate changes, and you basically use, K is a constant, and it's going to be the same in both particular reactions. And you basically say rate is equal to K times the concentration over rate is equal to K times the concentration. Because these are constant, we cancel them out. This is constant, we cancel it out. We have rate 2 over rate 1, and we have this to the x over this to the x. We solve for that, and we get 4 equals 2x, and we figure out what x is. And so you can do the same thing by inspection or by whatever method you want. The point is you have to determine x and y experimentally. All right, something else to note about these rate laws is that this K, basically the units on K changes depending on how many A's and B's you have in this. What these exponents are going to dictate what the rate constant is. And so for a zero order reaction where rate is equal to K times A to the 0, we get rid of the A. The units on K are molarity per second. For first order, rate is equal to K times concentration of A to the 1. It's per second. For second order, it's molarity per molarity per second. For third order, it's per molarity squared per second squared. And so you can memorize this. I wouldn't recommend it. Basically, this comes down to an algebra problem. It basically says rate is always going to have units of molarity per second. K, the units are going to change. These guys are always going to have units of molarity. And so depending on what M and N are, those are going to dictate what this X is. It's basically this needs to cancel out all of the M's here but 1. And so at whatever M plus N is, subtract 1, that's what your X is going to be. It's basically saying, this X minus 1 should be on the bottom. That's going to cancel out to get rid of these guys. And so, yeah, M's must cancel until you get molarity per second, so that gives you the units. You can also use the units to figure out what the order of the reaction is and potentially what the rate law is, depending on the number of reactants. And so this is not just an academic Gen Chem exercise. This is something that is used constantly in the literature. And so here's a rate law analysis of water oxidation on hematite surfaces, trying to do catalysis on rust, essentially. And so here you can see a rate law. It looks slightly different, but it is just literally change of concentration, in this case pressure, over time, is equal to negative K, which is the rate constant here of whatever species, times the pressure or concentration of something to an exponent beta in this case. And so, yeah, this is a peer-reviewed publication describing it. What's fun is these rate laws, when people try to determine it, it's contentious. And so here's another paper that came out 5 years later that said, questioning the rate laws in the analysis of water oxidation catalysis on hematite photoanodes. And so basically arguing maybe what they proposed wasn't right, maybe it's something else. And we have other things like, phenol oxidation in supercritical water. You can see these rate laws get a little bit complex. So here's rate is equal to rate constant times concentration times concentration times concentration. There's the exponents. In this case, they use A, B, and C. We used X, Y, but the same idea applies. And so you can see here we have even more complicated concentration change over time is equal to rate times concentration, so on and so forth. But it's the same idea. It's like trying to figure out the rate constant for a reaction allows you to compare and mix and match how competitive reactions happen. So again, not just an academic exercise, but this is if you work in the world of catalysis or chemical reaction rates, these are the things you care about. All right, so let's dive into our clicker questions. Unfortunately, you guys have noticed that we do not have clickers. We can't do this live, so I'm just going to suggest you guys pause it. You go through this reaction. But one thing I'm going to note is that we have, several questions ahead of us. I'm going to dive right into the answer, but I will give you guys a moment to pause, wrestle with the question, figure out your answer, and then we will go through and answer it from there. So pause, figure out an answer. All right, so the answer for this question is E. Not enough information to answer this question. Why? Because we don't have anything to figure out what the exponents on A and B are. And so we know our rate law, rate is equal to rate constant. And so it can't be A because there's no rate constant there. These have rate constant times concentration of A to exponent, B to exponent. The problem is we don't know what those exponents are. And so the general representation, C, is correct-ish, but without knowing X and Y, we do not know what the rate law for this reaction is. And so this one would be the general representation, but we don't have enough information. We need to know something else about the reaction. It could be B, it could be D. We don't know until we have experimental data. So pause for this one. Go ahead and answer. All right, what is definitely true about a faster reaction? So we have one reaction that goes faster than the other. And so what could we say about that reaction? The rate is larger, the rate constant is larger, there are more reactants. This really gets to the rate law equation, right? Rate is equal to the rate constant times the concentration. So if a reaction is faster, I mean generally faster across all concentrations, we can definitely say the rate is larger. And so A1 for sure is correct. Looking at the rate constant, looking at the concentration, we don't actually know if these two are larger. And so the reason is the rate of the reaction is dependent on the rate constant K times the concentration. And so we can have a fast rate two different ways. One is have a whole bunch of concentration, which is this, but have a small rate constant. The other one is we can have a large rate constant, but a small concentration. Both of those will give you a large rate. Because remember, the equation is rate is equal to K times concentration. Concentration goes up, rate constant goes up, rate goes up. Or it could be both of them. Both of these could be right, but we don't know for sure. And so this line definitely changes the outcome of this. And so long story short, the answer is A. The only thing we can know for sure about a faster reaction is that the rate is larger, but we don't know which one of these two is causing that rate to be larger. All right, pause on this one. So which reaction is faster? And so we have X turning to Y, X turning to Z. We don't know anything about the rate laws, but looking at the graph, we can say something about which one's faster, right? The one that has the greatest change in X with respect to time. So X to Z is faster. So the answer is B in this case. And so we don't know the actual numbers, but we do know that this slope change is much faster than this one. And so X to Z is happening faster. Next question is, which one has the larger rate constant? So pause and answer this question. All right, so what we don't know about this one is what the rate constant is. And so the answer is C, we can't tell. And so X is turning to Y, X is turning to Z, X is going way over time, X to Z is happening faster than X to Y, but we don't know what the rate constant or what the rate constant is because we don't know what the rate law is. And so for all we know in this case, that this first one, rate is equal to K times the concentration of X. For this one, K or rate could be equal to K times X squared, right? We don't know what role the concentration has in this, and so we can't definitively say anything about K or the rate constant of the reaction because we don't know what the rate law is. If we know what the rate law is, and if it was first order in both of these, then we could say, yeah, X to Z has a higher rate constant, but we don't know what the rate law is, and so we cannot determine that. All right, question 5, go ahead and pause. So in this question, we're given the rate law. And so since we know the rate law, we can figure out, what does change in A and B? How does that impact rate? And so this is kind of doing the opposite of what we did earlier when we had the table and we figured out the exponents X and Y. We can do the reverse process and we can say, okay, what would the effect of doubling the concentration of A have on this reaction? And so we can think about this as, let's just put a 2 out in front of the A, 2 times A, what does that do to rate? And so what's going to happen is 2 times A to the 2 is actually 2 squared times A squared. And so 2 squared is 4. And so it basically tells us whatever we do to A, we're going to exponentially increase that by squaring it. And so 2 to the 2 is 4. It means the rate is going to quadruple. And so the answer for this question is D. And so if we put a 2 there, 2 to the 2 is 4. That's the impact it's going to have a rate. It's going to quadruple the rate of the reaction. Similar question. We'll pause. All right, so in this case, if we half the concentration of B, you can see there's opposite sides of the equality. If this goes in half, this should go in half. If this doubles, this doubles. Whatever happens to B directly affects the rate proportionally, and so if the concentration of B is half, the rate should be halved. This is C is the answer on this one. Another version of this, go ahead and pause. So I kind of answered this with my answer to the last question, but it's the same idea, right? What does B do? So if we multiply B by 2, we are going to double this, which means rate is going to double proportionally. The answer is B. All right, pause again. So this question has a similar idea. It's saying A plus B gives us C. We have a rate law that looks like this, but we're thinking about this as an engineer, right? If you want to generate more product, you could say, how do I make this reaction go twice as fast, right? How do I double the rate of this reaction? And so I can look at this rate law and I can say, what can I do? And so looking at the equality here, if you want to increase this twofold, a couple different ways. You could increase K twofold or double K, or you could double B. And so the answer in this case is D. You could do either of those two things and this rate will double. So double this doubles, double this guy doubles. You could also increase each of them by a certain fraction, like 1.33 fold, and that would also result in the doubling, but that's not an option here. And so the answer is D, 2 or 3. What you can't do to increase the rate of this reaction is double the amount of A. You need A in the reaction for it to go, but changing the concentration of A because of this rate law right here does not change the rate of the reaction because it basically says A is not involved in the slow step. It has no impact on the rate of the reaction unless it goes to 0 and then the reaction completely stops. Question 9. All right, so this question, we're doing exactly what we did in the lecture portion of this, right? We have a tabulated table of data. We need to figure out what the exponents on X and Y are. What we know is it's not coming directly from just the stoichiometry here. It could happen to be that, but it doesn't necessarily come directly from that. And so we need this experimental data to figure out what that is. And so the way we do that is we take a bunch of different data as we say, okay, I need to know how X affects it, I need to know how Y affects it, and I need to isolate those variables. And so what I'm going to do is compare trial 1 and 2. X concentration is 1. That stays constant. If I change the concentration of Y twofold, what do I see happens to the rate? That changes twofold. What does that tell me? That concentration of Y is proportional to the rate. That means the exponent on Y has to be 1. And so already with that, we can rule out C and B being options. And so A or D are potentially, or E, depending on what the exponent on X is. But we figured out Y has to be 1, so A or D. So then we look at a different data set. And so we need to keep Y constant and see how the change in X. And so the pairing that gives us Y constant is trial 1 with trial 3. That stays constant. We double X, we see that the rate of the reaction doubles. That means the exponent on X has to be 1. They're proportional on both sides. And so we've ruled out D, we've ruled out E because the answer in this case is A. And so X concentration to 1, y to the concentration to the 1, and that gives us our rate law. And you can go back and double check this by saying, okay, if I double the concentration of y, the rate doubles. If I double this, this should double. This goes twofold larger, this goes twofold larger. Similarly, x twofold, twofold, yes, x goes up by 2, rate also goes up by 2. All right, so let's do a slightly different reaction. X plus 2y giving us 3z. What is the rate law for this reaction? Go ahead and pause and think it through. So you could go through the same exact exercise. You can keep one constant and figure out the other one. The thing I'll note is you'll notice question 9 and question 10. The data is exactly the same, almost exactly the same. And so you have the answer to at least one of those guys. And so let's just go through and do it real quick. If we look at, let's say we keep y constant, let's look at x. And so if y is constant, x here is 1 going to 2, 1 going to 2, just like we saw previously. The only way that happens is if the exponent on x is 1. And so we've already narrowed down. The answer is A or C or none of the above. Now we have to fix x, keep it constant, look at how y changes. In this case, y doubles and the rate doesn't change at all. That basically tells us y has no impact on the rate of the reaction. And so it says y is not involved in the slow step. And so what that tells us is the exponent on y has to be 0. And so the rate law for this particular reaction here is C. And so x, concentration doubles, rate doubles, y, concentration doubles, nothing happens to the rate, that has to be a 0. And you wouldn't draw it like this. You draw rate is equal to k times the concentration of x. And that would be your rate law for the reaction. All right, another one. This one's interesting. We'll just pause this briefly. This one might take a little bit of algebra, but it's kind of for fun. All right, so this one's a little bit interesting. This is interesting reaction type. And so let's take the scenario where we keep the concentration of y constant, and then we double the concentration of x, and we notice that the rate doesn't change. And so what that actually tells us is that this reaction is not dependent on the concentration of x in any way. And so x to the 0 is the only possible answer. It is none of these guys, so the answer is E, none of the above. But the question is, what is the actual rate law? And so we know its rate is equal to k times the concentration of x to the 0, so none of these can be it. But y gets a little interesting in this case. And so we take the other example, we say keep x constant, let's double y, see what happens to the rate of the reaction. And in this particular case, and this does happen in reality sometimes, you make the concentration of y larger and it actually slows down the reaction fourfold, which is unusual, right? It's like y is somehow inhibiting the reaction from happening, but that is entirely possible. And so if you go through the algebra on this, basically you need this to double, but the rate to slow down fourfold. The only way you can do that is if the exponent on y is a -2. Which again is weird, but it's basically saying 1 over y squared is what it would look like. And if you double the concentration of y, you're making it 1/4, which is weird, but this does happen sometimes. And so there are certain scenarios where algebra might be easier than the inspection, but inspection gets you the answer as well. And so in this case, y doubles, the rate decreases fourfold, and so that happens when y to the -2 and x to the 0 is so the overall rate law is rate is equal to k times the concentration of x to the 0 and y to the -2. All right, next question. I'll go ahead and pause. All right, so we're going the reverse direction. We have a rate law. We have our answer. We know how this reaction is going to unfold. It's k times x to the 1, y to the 2. What we're missing is numbers in this table. And so we have to look at a scenario. Okay, let's keep x constant. Let's change y. If y doubles in this case, what happens to the rate of the reaction? If I multiply this by 2, it should be multiplying the entire side by 4. And so the rate is going to quadruple. And so if it's a fourfold increase in rate, that means A should be 8. So the answer in this case is D. So just to reiterate, keep x constant. This doubles. If we double that, we have a 2 here. 2 to the 2 is 4. It's going to be a 4-fold increase. It's going to go 4 times as fast. 4 times 2 equals 8 molarity per second. The answer for A is 8. Doing another question, we have a rate law kx to the 1, y to the 2. We want to figure out what b is in the table here. And so we can do the same thing. Let's hold y constant, and let's see how x is going to affect this reaction. And so we want to figure out what this value is here. That's constant. This guy doubles. What happens when we double x here? It means the rate is going to double. And so the rate is going to go from 2 to 4. And so this is constant. This doubles. X to the 1 means it's going to double the rate. The answer is C in this particular case. All right. So we can figure out rate laws from those tabulated values plus the reaction. But we can also figure out a rough idea what the rate law is based on the units of K alone. And so the units on K rate constant is molarity minus 2 seconds minus 2. Which one of these could it possibly be? Pause and answer that question now. The answer in this case is D, all of the above. So this is the units for a third order reaction. How do we know that? Well, we know the units on rate are always molarity per second, right? M on top of S. And so we need the stuff on this side to cancel out, so it gives us that M over S. The only way to do that is if we have molarity minus 2 here on the K, we need the molarity 3. And so in all three of these cases, molarity times molarity squared gives us molarity to the third, molarity to the third, molarity to the third, which means we need 2 molarities down here to cancel with those molarities to give us overall molarity per second equals to rate. And so all three of these are actually correct answers because that algebra cancels out. And you can draw this out. Just put molarity per second here, molarity, molarity, molarity. K is always going to have a per second. The question is how many m's to the x's do we have? And in this case, it's going to be m to the minus 2 cancels out with 3 of those to give us molarity per second here. So yeah, rate law has to be experimentally determined. We can do it from the tabulated data. We can also gain some insights into rate law and the order of the reaction based on the units of K alone. All right, so that closes out section 12.3. Yeah, watch the next video and I'll post another video for section 12.4, which is integrated rate laws.